Swayam Prabha. Digital India. Educated India.
We are really going to start on the power electronic circuits today. So we'll start off from single phase rectifiers. So I'm going to start off with the simplest of circuit, which is actually a diode half wave rectifier. And first, to understand the basic working, I'm going to explain it with resistive load. Then we will go over to inductive load, then probably RLE load, and so on and so forth. So I am looking at a power supply which is normally 230 volts, single phase, 50 hertz AC. This is what normally we use if we are talking about single phase AC. So I am assuming that we are taking it from the power grid. And here I am going to put a diode, and here is the load, which is a resistive load, right? And when we consider the diode compared to 230 volts, 0.7 volts is very, very small. So I am literally going to take it as though it is ideal diode, hardly any voltage drop across the diode. So diode voltage drop, V forward voltage drop for the diode, right? I am assuming to be approximately 0. I am not going to take into account that 0.7 volts because compared to 230 volts AC, this is negligibly small, right? Now, if I draw the waveform, I am going to have basically a sinusoidal voltage that is being applied to this particular diode circuit. So diode will conduct whenever I am going to have positive here and negative here. When it is forward biased, it is going to conduct, and that will happen only during positive half cycle. So I am going to have essentially start conducting exactly at the beginning of positive half cycle, assuming that the forward voltage drop is negligible. Forward biasing voltage I am assuming almost as 0 volts, right? Of course, you require 0.7, but I am assuming that that is negligible. So I am going to have the diode conduct, and I am going to have the diode stop conducting exactly at this point. So this is actually the current, I. So the current is exactly going to follow the wave shape of voltage itself. There is hardly any difference because I am going to have essentially V, if I call this as VAC. So I should say VAC equal to V load when diode is conducting, right? Which is also incidentally equal to R multiplied by I load, if I may call this as R. So because of which I load is going to be whatever is my VAC divided by R, so the wave shapes are exactly similar. And if I try to look at the load voltage, I am going to have exactly until here the load voltage will appear, and after that it has to be 0, right? This is how the voltage has to be. I have to have essentially 0 voltage whenever it is reverse biased. So this is between when omega t, if I say this is omega t, when 0 to omega t until pi. And I am going to have V load equal to 0 when omega t is between pi and 2 pi. Right? So this is going to be the load voltage. So I should say this is supply voltage and this is load voltage. Right? And this is pi and this is 2 pi. right? So I can calculate, of course, you guys might have done it already in some other course, that 0 to pi Vm sin omega t d omega t 1 by 2 pi, that is averaged over one complete cycle. This is what is going to be my V DC, or I should say V load average. What is the output DC value of voltage? This is going to be the value. So if you calculate this, you will get it to be Vm by pi. Right? This is going to be the value of voltage that I am getting from the half wave diode rectifier, provided I have a resistance load. Right? And if I try to look at Im or I load average, so it has to be Vm by pi R. Right? Clearly. Because it is only related by the resistance, nothing more than that. So obviously, although this is an average DC voltage, there is DC component as well as AC component. I am not going to have the voltage, completely steady. It is continuously oscillating. In fact, it is going from zero value to peak value and again zero value, and it persists in zero value for another half cycle. So it's not a steady DC voltage. So if I apply this to, for example, a DC motor, it is not going to perform as well as if I connect a battery whose value is Vm by pi. There will be a difference in terms of the operational characteristics of a DC motor which is supplied with a battery of voltage Vm by pi versus this kind of voltage waveform, because for quite some time there is not going to be any current. If there is no current, clearly it's not going to develop any torque. If it will not develop any torque, it has to essentially come down in terms of its speed. At least for a short while, it will come down, depending upon the inertia, how quickly it comes down or how slowly it comes down. Right? So this is the way the waveform is going to be. Now if I look at the current here on the AC side, if I may call this as AC current. AC current is same as whatever is going through the load. They are connected in series. So obviously this is not only the load current, this will also be the supply current. It can't be any different. Right? So I'm going to have the supply current now not completely AC, it is DC. I hope you understand. What we mean by DC is it is unidirectional. So I will essentially have a current waveform repeating itself like this. For some time it is 0, again it will repeat itself. This is the way I am going to have IAC waveform with respect to omega t. Which means, by chance if I have a transformer in the input side, normally the transformer accumulates flux during the positive half cycle and then it will, give back the flux during the negative half cycle. Now, it will essentially go on accumulating flux if it doesn't have sufficient time to give away the flux. There is no current, right? Because of which during the other half cycle, so it can result in saturation of the transformer. Whenever I pass DC through a transformer, I can expect that the core is not able to get the flux and deflux. Defluxing will not happen properly, effectively, and that is the reason why half-wave rectifiers are not recommended in those circuits where I am going to use a transformer. Because if I use a transformer, the transformers can normally get saturated because it will carry only unidirectional current, not bidirectional current. Right? So much so for half-wave rectifier circuit with a resistance load. Right? Let us try to look at the circuit with RL load. So I am having a diode, I am having R, I am having L. Right? And I am going to have a sinusoidal voltage here. Right? Now, Again, I'm going to have 230 volt single phase, 50 hertz AC. Right? And I'm assuming again ideal diode. No doubt. Okay? So, when the diode is conducting, and if I'm assuming that the diode is not having any forward voltage drop or negligible voltage drop, so I should say when diode is conducting, I am going to have VAC equal to V load. If I say this is what is V load, I should say VAC equal to V load. Right? And V load I can write it as Ri plus L di by dt. If I am saying that I is the current that is passing through this particular circuit. So I am going to show as though this is the current I that is flowing. Load current I that is flowing. Right? Now, if I say that initially, let me draw the waveforms as well so that it will be clearer. So this is my AC voltage that I am taking up. Okay? Now this is of course 0, pi, 2 pi. I am probably going to have the current rising from some value. Say from 0 value it is rising slowly and it will go on and on. How long will it rise is the question. Right? Because when it reaches maximum, that is where the rising ceases. After that it will start falling. So I should write VAC minus Ri equal to L di by dt, and di by dt will be equal to 0 when VAC equal to Ri. From this equation I can say that is the maxima. Wherever the maximum occurs, at that point I am going to have VAC equal to Ri. So let us say probably at some point it reaches maximum. And then from here it is going to fall. It will fall further. Please note, I have not made this particular value exactly coincide with the zero crossing of the sinusoidal voltage waveform. The peak will also not coincide with the peak of the voltage waveform. Please note that the peak of this voltage cannot coincide exactly with the peak of the sinusoidal voltage waveform. That would happen if and only if I am going to have inductance equal to 0. Previously, whatever we drew was for pure resistive load. In pure resistive load, the voltage peak and the current peak were exactly coinciding with each other. Whereas, in this particular case, I am actually looking at VAC minus IR. In the previous case, that was equal to 0 because there was no inductance. But in this case, it is not equal to 0, it is equal to L di by dt. So, whenever I supply a voltage, now it is going towards two work. One work is dissipation of energy in resistance. The second one is storing magnetic field energy in the inductance. So it is doing two work, and in that the magnetic field energy can be retrieved. It is not like resistance loss which is gone. So I am going to have to retrieve that energy. So when I am retrieving that energy, let me draw the voltage waveform as well. So let us say this is current. So IR should have exactly a similar wave shape. It is only a scalar multiplication. So I can draw IR somewhat like this. Maybe my IR is somewhat like this. Right? And when I draw IR further, I should probably draw it somewhat like this. Right? I times R is basically a scalar multiplication of the current with resistance. So IR will exactly have the same wave shape as that of the original current I have drawn. So let me mark this as IR. Now, VAC minus IR is L di by dt. Yeah. We are going to come to that. That's the reason why I am giving so much of explanation. When I am having V minus IR, this is the difference between VAC minus IR. Am I right? This is IR, so this is VAC minus IR. That is going towards L di by dt. So that area indicates the amount of energy stored in the inductance. So I am essentially looking at this portion as, because I write L di by dt equal to VL and this is VL. This particular portion what I have written is VL. I hope you understand. That is what is VL. Because VAC minus IR. That is what is VL. So VL, so if I say integral VL dt, that is what I have shown as the area. So the area, this is the shaded area. So this is essentially L di integral. Am I right? So indirectly, I am showing the energy stored in the inductance by this shaded area. Now, this is L di by dt no matter what, whether I am going to have the resistance drop dominating over the AC voltage or vice versa. Please note here that the AC voltage is dominating over the resistance drop. Whereas here, please note, I am going to have this as the resistance drop, whereas this is the AC voltage. So AC voltage is subdued as compared to the resistance drop. So if I look at the difference between these two, I am going to have it as though this is actually the shaded area which is coming as the difference between IR and VAC. So if I call this as the positive area, I would have this to be the negative area. You get my point? So whatever the inductance has accumulated during the portion of AC voltage being greater than IR, all that energy is returned when IR is dominating over the supply voltage. Right? So the crux of the matter is, whenever there is a larger amount of energy that was available, the resistance was dissipating part of it, rest of it was being stored by the inductance. And when there was a shortfall in the voltage, that was being supplied, the inductance could join hands with the voltage, AC voltage supply, and it was trying to supply whatever was required by the resistance. Right? To look at it in terms of more mathematically, I would say when the current is flowing like this is plus and this is minus. Similarly, this is plus and this is minus. Right? This is how it is. Fine? That is the reason why the diode is getting forward bias, because I am having plus here and minus here. So obviously this is plus. And if I may call this as the common ground, this is the common ground. Agree? Fine? Now, when I am having this current increasing, when this current is increasing, which is shown here with this red color, right? It is increasing. When the current is increasing, this is plus and this is minus. Di by dt is positive. This di by dt happens to be positive. After some time, what happens is VAC minus RI becomes 0. The current has increased quite a bit. VAC minus RI has become 0. Because it has become 0, the current has reached its peak. Beyond that, the supply voltage is not in a position to supply any more energy to the inductance, because all the energy that it is giving is going towards dissipation in the resistance itself. You are not going to have any further energy left over. At that point, now inductance will say that, okay, I have stored all the energy, now let me return the energy. Because it cannot get any energy, not that it is being very generous. It cannot really get any more energy. So it is going to start giving back. When it gives back, it is essentially getting defluxed. You get my point? It is getting defluxed. When it is getting defluxed, phi is going to decrease. If phi is decreasing, I has to decrease. Both of them are dependent on each other. So current is going to decrease. When the current decreases, di by dt becomes negative. When current is decreasing. When current is decreasing, di by dt becomes negative. So if di by dt becomes negative, this will become plus and this will become minus. I hope you understand this. Obviously, I am going to have plus and minus completely reversed. Right? So the inductance now is not like a load. It is rather acting like an energy source. It has saved some energy. Now it is giving that back. When it is giving back the energy, please note, this is minus plus, this is plus minus like this. Both these things become additive. You understand this? The inductance is having plus minus in such a disposition that I am going to have that added to whatever is VAC. Both of them are added together. Now, I have to look at the overall voltage that is visualized by the diode. Whether that is going to be positive on its anode and negative on its cathode or not. Now the inductance is pitching in. The overall voltage is definitely going to look positive because of the fact that the inductance is also returning energy. So until the inductance is returning energy, the diode will be able to retain the current in the same direction. Because of the inductance voltage, it will be forward bias. That is the reason. So that is one reason why the current continues beyond the zero crossing of the supply voltage. The higher the inductance, this point will get delayed further and further. The lower the inductance, I will have obviously less and less amount of current flowing during the negative half cycle, or the duration will get shrunk. Is this clear? Because if you understand this concept, any RL load further we will be discussing will become a cakewalk. This is the first concept you have to be really clear, especially in RL load. Why, despite a diode sitting there, why I am having actually the current in the negative half cycle. It is continuing in the negative half cycle. And how long this is going to continue? That depends upon how dominating the inductance is. So this has to be solved for only, by complete solution of the differential equation along with the particular integral derived corresponding to Vm sin omega t. It's not going to be easy because it will start off with a transient and then it will go through, you understand, this is starting from zero, agree? So in this case, there is no transient. When we come to full wave rectifier, we will see a transient. Anyway, so in this particular case, we are going to see that the initial condition is 0. I of 0 is 0. That's not a problem. So it is easier to solve in that sense. You will be able to solve this by solving the differential equation Ri plus L di by dt equal to Vm sin omega t. Right? Where omega t will be from 0 degrees until whatever point this is conducting. This is beta, if I may call this as beta. This point is where the conduction ceases. So how long this conducts heavily depends upon what is the value of inductance relative to the resistance. Both of them relative to the resistance. Is this clear? Okay. So RL load becomes slightly complicated because of this reason. And of course, if I try to look at the voltage, my voltage is still the same as far as supply voltage is concerned. And if I try to look at the current, whatever we have drawn just now, so I'm going to have the current maybe reaching a peak somewhere and then finishing it somewhere here. So this is going to be IAC as well as I load. Both of them are the same. So this is IAC. Both of them are obviously the same. Load voltage is clearly, how much is the load voltage? Load voltage should be completely all this voltage, because we are writing not only VL, it is VR plus VL, and then it will come here also until here. So this entire portion will be load voltage. I will get definitely some portion of the negative voltage as well. And it is not going to be easy really to calculate this particular voltage, because this beta is not set in stone. The beta is going to change. The beta is not going to be exactly a constant. Depending upon R and L value, it will change. If inductance changes, correspondingly beta will change. So I should be able to write this as V average load will be from 0 to beta 1 by 2 pi Vm sin omega t d omega t. This is how the load voltage will be. Right? Okay. So shall we proceed to RLE load? Is this clear? Any questions on this? Yes? Exactly. Wherever I am going to have VAC equal to IR. So maybe what you say is right. The way I have drawn, I should show it as though this had reached the peak here and this is IR. So this is IR peak. IR peak must have happened wherever the current was reaching the peak. You understand? Because IR has to meet with the supply voltage. Wherever it meets with the supply voltage. Right? Okay? Let us now try to go to a half-wave rectifier with RLE load. So we are basically talking about a diode rectifier, a sinusoidal voltage. I am going to have R, L and E. This is typically the case whenever I want to charge a battery, right? The battery will always be connected like this so that the charge is getting into, the current is getting into the positive terminal. Positive terminal of the battery. Only then it will get charged. Right? So this is again 230 volts, single phase, 50 hertz, AC. And this is the diode. Let us say I take maybe a battery of 230 volts itself. Right? DC. Now obviously, when I am actually having the voltage waveform like this is 230 times root 2. The peak is 230 times root 2. So that is approximately 325 volts or something. Right? So this is going to be 230 root 2. So if I take 230 volts, it will be somewhere here, divide by 1.5, right? So it is